Hi, everybody. We are here in section 4.4. Yeah, and we're going to talk about L'Hopital's rule. Take a look at this. We've got limits again. And you might be asking, Dr. Ledmo, I thought we were done with those. Why are we doing limits again? Well, L'Hopital's rule is a nice tool that will help us solve limits that we haven't been able to do before, specifically limits that are in an indeterminate form, like 0 over 0, or although there are lots of indeterminate forms that we'll look at today. And so why didn't we do this earlier? Well, L'Hopital's rule is going to make use of the derivative, which we did not know earlier when we were working with limits just themselves. And so, yeah, our knowledge of derivatives is going to help us evaluate some interesting limits. And before I start working through this stuff, I would suggest you guys go ahead and look at the 3 Blue 1 Brown video. It's on that YouTube playlist. I would start it at 10 minutes and then go to 16.5 minutes. But there's a nice animation there that shows you why L'Hopital's rule makes sense intuitively. So go ahead and do that and then come back and we'll get into this stuff. Okay, here we go. So you just looked at L'Hopital's rule and you see L'Hopital's rule means the limit as x approaches some interesting number that you're approaching of this ratio of two functions the ratio ends up being equivalent to the limit as, you know, these derivatives approach the same value. And, you know, here is a sequence of equivalent limits that kind of gets down to there. Yeah, pretty cool. But I think we should just get stuck in here and start working through some examples. So if we wanted to evaluate this limit, we got the limit as x approaches 0 of 5x minus 2x over x. And yeah, if you put in 0 everywhere there, you're going to get 0 over 0. So we are in an indeterminate form. That's something that you need to check every time. But since we are, you know, in that kind of a scenario, that means we'll be able to employ L'Hopital's rule. And when I'm actually applying L'Hopital's rule, I like to write a little LH over the top of the equal sign to remind myself that, you know, what I'm getting right now has definitely been changed from before. But yeah, if I take the derivative of the top, we're just going to have a 5 minus 2 cosine of 2x by the chain rule, and then over 1. And now if I plug in x equals 0, we get 5 minus 2 times the cosine of 0, which is 5 minus 2, which is equal to 3. All right, so a limit that we would not have been able to do before turns out to be not so bad when we employ L'Hopital's rule. Here's L'Hopital's rule in Earnest. What's important to pay attention to here? Well, there are a couple ways, a couple forms that we're on the lookout for here. This first part means that we've got an indeterminate form that looks like 0 over 0 because we've got a ratio of f of x over g of x. And if the limit of the top is approaching zero and the limit of the bottom approaching zero, that means we've got this kind of indeterminate form. But this framing of L'Hopital's rule also includes indeterminate forms that look like, whoops, infinity over infinity, or negative infinity over infinity, or, throw a negative sign wherever you want. Yeah, these are also indeterminate forms where we can apply L'Hopital's rule, which just boils down to taking the derivative of the top and taking the derivative of the bottom individually. This is not the quotient rule. Yeah, it means that the ratio of those two functions as you approach the limit is the same ratio as the derivatives, which is pretty cool. This rule does work for one-sided limits and for limits to infinity. So that's great. Let's keep going. We're gonna, oh my, this is big. There we go. We're gonna, evaluate some more limits, and they're going to get more and more interesting as we go on. Okay, so this one, again, we would get 1 minus 1 over 0 again, which, that's bad. But yeah, here, let's go ahead and click this real quick. We're taking the limit of this function as, oh man, the last time I had this open, it had, there was a cool thing that I'd never seen before, but now it's just making me look silly. It actually had an open, there it is, look, look, look. Removable discontinuity. GeoGebra is growing in power. I've never seen that before today. Anyway, this function looks like it's completely continuous, but there is a removable discontinuity here. And, notice that we can change A and get a lot of different limits. But yeah, the idea is we're solving what does this function approach from the left and from the right when we approach x equals 0. Okay, so let's go back and we'll do L'Hopital's rule. Because we are in a 0 over 0 scenario. Yeah, so L'Hopital's rule would tell us that the limit as x goes to 0 of the derivative of a to the x will be ln of a times a to the x, and the derivative of x will just be 1. So that allows us to plug in 0 for x, and we just get ln of a, since a to the 0 is just going to be 1. And so, yeah, what I had on the GeoGebra demonstration is, if you put in a point, if you have a point at 0 ln of a, it perfectly fills in that removable discontinuity. Cool. All right. Okay, that one's kind of boring. Maybe this one would be good to, take a break and, well, actually be involved, take a break from taking notes and try to evaluate these on your own for a minute or two. And then I'm going to keep going, and you can unpause when you feel like you're ready to look at it. Okay. Yeah, for this one, we would see that this is going to infinity over infinity. And you might even want to think of this as like a struggle between functions, where the top function is racing off to infinity at a certain rate, and the bottom function is racing off to infinity at a certain rate. But if we think about this, the exponential function is going to grow a lot faster than just a measly old polynomial. So what do we expect in this? We expect e to the x to win, and probably this entire limit just go off to infinity. But let's check what happens when we use L'Hopital's rule. We're in an infinity over infinity situation, so we are okay to employ L'Hopital's rule. So if we take the derivative, we get e to the x 10x minus 3 on bottom. And, oh well, we're still in a scenario where we're going to infinity over infinity. So we can do L'Hopital's rule again. E to the x over 10 minus 3. And now, legitimately plugging in infinity just takes us off to infinity proper. And yeah, we get that as the result of our limit. For the next one, if we plug in 0, we get 1 minus 1 on top and 0 on bottom. So this one goes to 0 over 0. And so we're going to do L'Hopital's rule. Yeah, limit as x goes to 0 of taking the derivative of negative cosine is going to give us a positive sign. And on the bottom, we would get 6x plus 7. Okay. Notice we should test to see whether this works. And if we plug in x equals 0, we get 0 on the top and then 7 on the bottom. And so 0, good grief, sorry. 0 is our actual limit there. There's something funny that can happen if you didn't realize that you were supposed to stop here and get 0 for a limit. If you were to apply L'Hopital's rule another time, feeling like, well, the top's 0 and the bottom's maybe 0, I don't know. You can only apply L'Hopital's rule when you're in an indeterminate form situation. If you applied it again for this part, you would get cosine over 6. And then when you plugged in x equals 0, you would think that 1/6 is the answer. But you were already supposed to have stopped. You can only apply L'Hopital's rule when you're in an indeterminate form situation. Okay. Moving on to example 5. Ooh, this doesn't look like L'Hopital's rule problem. There's no fraction. Well, let's take a look at this. If we're approaching 0 from the right, let's think about what each of these functions would approach. Square root of x would approach 0, and the natural log of x would approach negative infinity. So we're in a scenario where we're in this alternative form that is actually indeterminate, where we've got 0 times some form of infinity. And when we're in this situation, eventually we're going to want to use L'Hopital's rule, but we need to write this as a quotient. And so probably the easier one to put on the bottom would be the square root of x. And so if we rewrite this as the limit as x goes to 0 from the right, the ln of x over x to the negative 1/2 power. So 1/2 power because of the square root, but since I put it on the bottom, I need to make it, a negative power. I think now, if we put in 0 on the top, we're going to negative infinity. Like last time. And if we put in 0 on the bottom, well, again, and you might even want to think about that x to the negative 1/2 as 1 over the square root of x. But that x to the negative 1/2, the denominator would be going to 0. So the entire fraction would be going to infinity. So we're in a scenario where we've got negative infinity over infinity. And so we are in an indeterminate form where L'Hopital's rule will be appropriate. So let's see what happens after one application of L'Hopital's rule. Taking the derivative of the natural log will give us 1 over x, and taking the derivative of that mess will give us 1/2, negative 1/2, x to the negative 3/2. Oof, that's not great. Well, let's keep working with this. I think now that we've got some powers of x here, we might be able to bring things around. All right. What I would like to do is now take it out of this quotient form. Let's bring the denominator up into the numerator so we can express this as a product. So we've got the 1 over x. Why did I make it all slanty? 1 over x times, we've got that negative 2 from the negative 1/2 on the bottom. And we've also got x to the 3/2 power. Now, 1 over x and x to the 3/2 power is going to allow us to, combine those. 1 over x is just x to the negative first. So we have negative 2 times x to the 1/2 power, or the square root of x. And shoot, I should have written the limit again. Because we haven't substituted in 0 yet. But now we could. And this thing's just going to go to 0 overall. Cool. Yeah. All right, let's keep going. Here we get to example 6, and yeah, I'm just making sure I got that. Yeah, we're cool. All right. All right. We got indeterminate forms, some new indeterminate forms. There's actually another video that you guys could watch. It's, fairly short again. For this one, it's by Mathologer, and if you wanted to watch it, it would be from 6 minutes to 10 minutes. But yeah, it's just an exploration of different indeterminate forms and how to get indeterminate forms that look like this back into things that look like quotients, so that we can actually do L'Hopital's rule on them. In this example, we've got something that looks like infinity minus infinity when you substitute in 1, because this one's going to approach 0. This is going to approach something over, 1 over 0 again. And we're going to work to get this into one quotient that we can apply L'Hopital's rule. All right, coming back, let's do this. Now, in order to evaluate this, we're going to just need to make common denominators. And so on the top, we'll have x times the natural log of x minus 1 times x minus 1. And the bottom will be x minus 1 times the natural log of x. Okay. Yeah, let's, at this stage, if we were to substitute in 1, we would still have 0 on the bottom. And, okay, we would have 0 on the bottom, and we would have 0 on top, right? Because we'd have 1 times 0 minus 1 times 0. So at this stage, we are in a 0 over 0 indeterminate form. And we could continue solving this using L'Hopital's rule. This L'Hopital's rule is going to be a little bit messy. It'll be okay. We can do this. Okay, so on the top there, if we're taking a derivative, we've got x times the natural log of x, which is going to be a product rule. So we take the derivative of the first one and multiply it times the second to get natural log, and then we're adding the first times the derivative of the second, which would be 1 over x. Okay, so that's a product rule for the first one. And then the next part, we would just have, negative x plus 1 if we were to distribute that negative 1. And so taking the derivative, we just get a minus 1 for the minus x part. Okay, so we did the top, and then the derivative of the bottom, again, that's going to be a product rule, where we take the derivative of the first term and multiply it by the second. So we get ln of x again, and then we add that to x minus 1 times 1 over x, the derivative of the natural log. Okay, well, let's see what kind of a scenario we're in now. I think we can do some simplification here. On the top there, we're going to get x times 1 over x, and that's just going to turn into a 1. So 1 minus 1 is just going to cancel out, and all we're left with is the natural log on top. On bottom, we're going to have the natural log just hanging out. And then this part will be distributed so that we get 1 minus 1 over x. Okay, and now if we were to plug in 1, we get ln of 1 is 0 on top, and we get 0 plus 1 minus 1. So we'd get 0 on the bottom again. So we're not done. Okay, we keep going. Let's take, we're again in the 0 over 0 indeterminate case. We're not going to let that get us down. Taking derivatives, the top and bottom again, gives us 1 over x on top, 1 over x minus Well, and it's going to turn into a plus because we would be bringing down the exponent of -1, 1 over x squared. And so we're very, very close to being done. If we take a common factor, or I mean, if we just multiply top and bottom by x, let's just say that, we would get 1 on the top. And 1 plus 1 over x on the bottom. And so now we could, yeah, plug in 1 and get 1/2 as our answer. We did it. Okay, so on that one, big takeaway. We're always hunting for a form that's a quotient, where we get something that looks like 0 over 0 or infinity over infinity. That's when we can apply L'Hopital's rule. We did some product rule along the way and figured out that we needed to do L'Hopital's rule again. And after the second application, we simplified what we had and got our answer. So L'Hopital's rules. Let's keep going. Example 7 and example 8 are going to be the tricky ones. Okay, here we have example 7. This one might look familiar. I put it on one of your activities earlier. I don't know, it might have been the first or second, maybe third activity. And I guess it looked a little bit different than this. I think on that activity, I had it phrased the other way, where instead of going to 0, it was going to infinity, and this was a 1 over x, and this one was just an x. But we're actually going to get the same thing. This is another fancy way of defining the number e. So hopefully we get e at the end of this. If we look at this as an indeterminate form right now, what would happen if we plug in 0? We would get 1 to the infinity power, which is an indeterminate form, but we need to make it look like a quotient. But really, it looks like we've only really got like one function here. How are we going to make that into a quotient? Where we can take the derivative of the top and the derivative of the bottom, and it actually makes some sense. Well, this is one where we're going to have to use a logarithm to bring that 1 over x out of the power. So my first step here, I'm going to write this as y equals the limit as x goes to 0 from the right of this entire function. Because that y is going to allow us to keep track of the natural log along the way, and eventually we'll have to undo the natural log with an exponential function. So the strategy here is take the natural log of both sides, and know that we would be taking the natural log of the entire limit part, but due to that composition theorem that we looked at when we were looking at limits, I can bring that natural log on the inside. So I'm going to write it like this, where we've got the natural log of 1 plus x to the 1 over x. And now that this exponent is on the inside of a natural log, we're going to be able to rewrite this as a product where we've got 1 over x times the natural log of 1 plus x. And then we can make this into a form that will be L'Hopital's rule like if we, let this thing become a quotient. Recognize that if we were to put in 0 into either of the expressions, we would be going to an indeterminate form, 0 over 0. And so then we can apply L'Hopital's rule. And the bottom's going to work out really nicely to just be a 1. The top is going to be a chain rule, where we take the derivative of the outside, giving us 1 over 1 plus x, and we multiply that times the derivative of the inside, which is just 1. So in this case, we're taking, the limit as x goes to 0 of this fraction, basically, and that's just going to be 1 over 1. So, well, hold up. I shouldn't put a box around that necessarily, because this whole string of equal signs tells us that the natural log of y equals 1. Yeah, so I wrote that natural log of y down to remind me at this part, if we want to figure out what this limit actually is, we need to get back to y, which tells us if we exponentiate on both sides, we get y on the right-hand side, and we get e on the right-hand side. So, yeah, e is this limit. So, yeah, we had to use a logarithm to get this exponent down and then into a quotient. Very similar strategy here for number 8. Here we've got x to the x, that's a weird function. But again, we would be in a situation, now the limit looks like 0 to the 0 power, which is another indeterminate form. We're going to use a log. So we've got, y equals this limit. Natural log of both sides. Use the property of logarithms to bring that x out front. And then, this is starting to look like one of the ones that we had done before. I think, if we make this so that we have, oh no, not L'Hopital's rule yet. We're still getting it into a quotient. The natural log on top and 1 over x on bottom. Then we can do L'Hopital's rule, because this is now going to negative infinity over infinity. Have the ratio there. So we do L'Hopital's rule. And get 1 over x, and then minus 1 over x squared. And so similarly to that other time, we can do a little bit of simplification. And 1 over, x squared, dividing by that means like multiplying by x squared. And so, literally we have this, which turns into limit as x approaches 0 from the right of just negative x, which turns into 0. Wait a second. feel like that's wrong. Oh, it's wrong because I'm not done yet. Good grief, Ian. Okay. Remember, back here, we had the natural log of y, and that's what equals 0. So, ln of y equals 0 means that y should be equal to 1. Again, you could, exponentiate on both sides. Boom, boom. Okay, that feels better. So now the limit is equal to 1. And that's what we put a box around. Okay, cool. Yeah, x to the x. This is not a function that you see every day. Isn't that weird? It's down and then comes back up. And then, skyrockets off into space. X to the x. But yeah, the limit as x approaches 0 from the right does indeed equal 1. And we just did that. Boom. Okay, that's example 8. Example 9. I mean, it's the same thing again and again. We're going to do another natural log thing. All right, I already did just 2 of those in a row. I'm going to punt on this one, save us all a little bit of brain space. Wait a second. That's the one I did. Oh my goodness. Does this happen to you guys too? On some of these pages, Hawk will never fully load the ebook and drives me nuts. But again, yeah, we do this thing where we get the y equals the limit part. Yeah, you use this to get it into a quotient, indeterminate form infinity over infinity. And then after doing a L'Hopital's rule, you get 0. And again, it turns out to be 1. I don't know why there's example 9. That one's boring. This one's fine, but also kind of boring. Okay, we're great. Example 9. Let's keep moving. Oh man, this is good, but it's again kind of review from stuff that we talked about last week. Calculus and curve sketching is section 4.5, but also there's going to be something new called Newton's method that's going to be in here. I'm going to save that for tomorrow, but Newton's method will be cool. The curve sketching thing is what we did last week, except with a few more steps. We're going to eventually find critical points and think about intervals of increasing or decreasing, or concave up or concave down, using those first derivative, second derivative tests. We'd be thinking about relative extrema, inflection points, all that good stuff eventually. But in order to get a nice curve sketch, there are some other things that you can consider, like the domain, any symmetry that the function might have. Think about whether it's periodic, and then, that would factor into sketching it. Identify intercepts. A lot of times this is used to kind of anchor the function so that you can, position it relative to the origin. And also plotting asymptotes, especially for rational functions that have horizontal or vertical asymptotes. Those can be useful to identify. And L'Hopital's rule would occasionally be useful, especially when you're looking for maybe horizontal asymptotes as x approaches infinity. L'Hopital's rule could be useful in those kind of situations. That's why this curve sketching part is after the L'Hopital's rule part, because in this part, L'Hopital's rule could be useful. So we're revisiting some stuff that we did last week, but now we're trying to do this a ton. One of the things I might suggest is go ahead and try these. If you've still got a decent amount of time left in the class, go ahead and try to do first derivative test, second derivative test. Think about if there's symmetry to either of these. Think about where it would cross, especially the y-axis. So, y-intercept. But yeah, with the intervals of increasing and decreasing and the concavity, try to sketch this as best you can. I'll try to do this quickly. Oh, I was actually thinking about doing this one by hand and then setting you loose on these two. Oh, how much time are we at? We're at 4:30 on Friday afternoon. All right, we can do a good job of one or two of these. Let's see how long it takes. I'm gonna do example 1, and then if there's time, we could practice some more on example 2 and example 5. All right, curve sketching strategy. I'm looking here, the domain would be all real numbers. This is just a polynomial. Does this have any symmetry? This part's odd and this part's odd, but this part's even, so not really. Yeah, this would go through, if we look at f of 0, that would just be 0. So this is going to go through the origin. And so maybe, yeah, actually for this whole time, I'll keep a graph over there. Yeah, let me do this in black so that when we get some new information about the curve, I can add it. So boom, we go through the origin. Let's find some critical points because there's not going to be horizontal or vertical asymptotes on this one. Yeah, let's take some derivatives. Yeah, first derivative would be 30x squared minus 12x plus 1. And we would set this equal to 0 to find some critical points. Setting that equal to 0 doesn't give us something very nice to factor, I don't believe. I think we get some weird stuff. Quadratic formula. Let me check. Yeah. What happened? I was zooming in. All right, let's bring this over. Yeah, this is gross. Actually, now let's keep going. Copy that, paste it over here. Yeah, quadratic formula, this stuff, get this, which turns into what? This is like 1/5 plus or minus square root of 24 over 60, which that could be simplified a little bit more, but roughly that's going to be. And so there's going to be 2 points, centered around 1/5, so it's going to be close to this in the x value range. But yeah, both of those should be positive numbers because the square root of 24 is going to be smaller than 12. So those will be two positive numbers. I feel like I had this plugged into GeoGebra at some point. Anyways, those are some critical points for our first derivative test. As far as the first derivative test goes, let's keep it pink. And we would say, yeah, this is 1/5 minus, all right, if we pulled out a square root of 4 here, we would have 2 times the square root of 6, which means this is the square root of 6 over 30. Okay. Square root of 6 over 30. So yeah, 1/5 minus the square root of 6 over 30 is the first one. And I'm recognizing that this is getting ugly bunched up. 1/5 plus the square root of 6 over 30 here. And what we would need to do is, plug in some values and figure out whether our derivative is positive or negative. How about, let's plug this thing into GeoGebra and it should be good. We can use that because I don't want to plug in those numbers. All right. Calculator, sweet. We started off with the function (10x cubed minus 6x squared plus x). And yes, I do recognize the irony of we're doing curve sketching. Why are you just plugging this into a graphing calculator? It's so that I can do the operations. We figured out that, yeah, the derivative was a thing, and that the derivative crossed at, some nasty points, but we were confident that they were going to be greater than 0. So that's cool. What we would want to do is plug in some test values, but from the graph of the derivative, we can tell that the derivative is positive over here, negative in the middle, and positive again. So I'm going to go back and just say positive, negative, positive, meaning that we've got increasing, decreasing, increasing on those intervals. So I don't know, if we want to use the results of the first derivative test, we would be increasing through here until we get to something where we decrease for a little bit, and then we increase again. And these are the two critical values from our first derivative test. So we already start to get a shape of the graph. To get a little bit more precise shape, we would use the second derivative test. So let's go ahead and write the second derivative down. That would be 60x minus 12. And we're going to set that equal to 0 to get some critical points for the second derivative. And this one would actually be easier. Here we just get x is equal to 1/5. Which was actually directly in the middle of these two x values because, yeah, we're symmetric around 1/5 here. So this one is going to be an important thing there. If we were going to do the second derivative test, we'd want to test a couple points on either side of 1/5. And this one is probably easy enough to just test 0 and 1. So If we test 0 here, we would get negative 12. So if we test 0, we get a negative number. And if we test 1, we would get 60 minus 12, which is a positive number. So this means concave down on this side, concave up on the right-hand side, and yeah, that would allow us to see that, yeah, concavity, we're going to be concave down over here. So this part is going to be actually curved, and this part's going to be curved this way, which is, kind of what you expect. We're working with a polynomial here, so we're not going to get too many surprises. I guess the final thing here is to make sure, we recognize maxes and mins. If the derivative changes from positive to negative, here we get a max, and here we get a relative min, so that, yes, there should be a max here and a min down here at each of those values. And if we go back and actually check our work against this original function, we do have a maximum here and a minimum there, centered around 1/5. So those are symmetrically spaced around 1/5. So we did a decent job graphing that function. I was a little bit aggressive with my curves here on my picture, but I did that so that, they would be visible. But yeah, this graph does not actually go below the x-axis again, which would have been something good to do. Yeah, one of the things that you could do is factor that original function. Let's use purple. If we factor that original function, we get x times 10x squared minus 6x plus 1. So yeah, that definitely does tell us that it goes through the origin again. This would give us 2 more numbers, possibly. Maybe not. Is this one factorable? Let's see, 10x squared minus 6x plus 1. I'm kind of thinking it's not factorable. We can tell that that function is not factorable because it doesn't cross the x-axis at all. If we put this into the quadratic formula, we would get 2 imaginary answers for our roots. So that tells us that the original function does not cross the x-axis ever again, which would warn us, don't come back down far enough to cross the x-axis again, if we were actually trying to curve sketch this thing. So the only x-intercept is just x equals 0. Okay, that's good. These ones, I have a feeling that I've gone too long. They're interesting. This one, I don't know. It might have an asymptote somewhere. Yeah, you could think about an asymptote as these things go on out into infinity, maybe. No, maybe not. Oh gosh. There's more that we could do with these curve sketching. And it's fun. It gives you practice with the first derivative test and the second derivative test and critical points and that kind of stuff. When the rubber meets the road, though, Those are just, you know, practicing the skills that we've recently learned. Um, Graphing calculators are really cool, and they're getting better all the time. Curve sketching is a little bit outdated. It's not bad to practice. You do get practice with useful skills, and you get a deeper understanding of those functions. But I'm gonna quit. And if I look at these and I decide to need to look at them the next day, you know, tomorrow, that's fine, and we can look at them tomorrow. But anyways, have a good day. I'll see you tomorrow. Yeah. Bye.